specifically. So let's see what this is about. Y'all ready? Y'all ready for the horror that is math? That's freaking awesome. Anyways, let's go.
All right, we're gonna finish this poor guy's second grade math homework. I know. Why would we waste our time doing someone else's homework? But it's not like it's advanced fourth grade math. This is second grade, which means it's only half as hard. So let's take a look. This is worksheet 1A. It says, we know that multiplying means making groups. Make groups for the following equations. And we can see over here on the right, we'll have to draw pictures for a few different multiplication problems. And that's super easy, so I really don't know what all the hubbub's about, in case you've never done something like this. 2 times 3, for example, is 2 groups of 3. So if we wanted to draw a picture to represent that multiplication,
You guys know that? 3 times 3. 2 groups of 3. Not 3 groups of 2, like some plebs might think. No, it's 2 groups of 3, just so you guys know.
we could just draw 2 columns of 3 dots each. We could count it up, see there's 6 dots, which tells us that indeed 2 times 3 is 6. So that's all we have to do. Now let's finish this darn homework. Let's see, the first one is 0 times 3 means 0 groups of 3. Well, let's come back to this one. The next problem is 0 times 8 means 0 groups of 8. 2 times 0 means 2 groups of 5.
This is a
What?
joke.
What? Bro, oh, if anybody shows this to Dina, it's so over. It's so over. How are we supposed to draw 1, 2, 3, 4 groups of no groups of anything? You might think,
0. What does that say in the top of the page? Can I zoom in? Enhance.
well, it's a little
Oh, he was zooming in. The zeros. Okay, so this worksheet is on zeros. But that's hilarious. We know that multiplying means making groups. Make groups for the following equations. 0 groups of 3. Draw a picture. How would you do that? Let's put our thinking caps on. How would you depict 0 groups of 3? All right, let's call it 3 apples, right? So there's 0 groups of 3 apples. Let's see here. Let's see. Do that. We'll do a little bit of that. We'll do a little bit of this, and a little bit this. All right. Oh, we got that there. There's our window, our box that we're drawing our groups of apples. And do a little bit of this. Let's see if we can make a nice looking apple. We'll go like that, and we'll go like oh, I can move it. That, bam. And we'll do another one right here, like that. Bam. And then we'll do this. Bam, 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 bam. And then we'll grab one of these. No, we'll grab one of these. And go like that. Bam. And something like that. Bam. Erase this. I don't know what happened. What's happening? Why is this? What the heck is wrong with this eraser, dude? What is going on here? Okay, I could draw. What the heck? This is a interesting new feature of whatchamacallit, I guess. Paint that I was unaware of. Go like that. Boom. And like that. Uh-oh. Uh-oh. Control Z that. Ah, I don't know. Control Z the last bit. God damn it. That. Oh, bam. Bam. Oh, bam. Okay. And then we'll do another one like that. Oh, bam. Like that. And sure. Oh, bam. Just go ahead and zoom. Just zoom. Drawing that to the leaf. Maybe we'll touch it up just a little bit. Oh, that doesn't come through at all. Erasing. That is so weird. I don't know what's up with the eraser there. That's the stupidest fucking thing I've ever seen. Alright, so we're gonna go bam. Okay. Okay. And fine. Very nice. I am an artist, as you can see. Alright, so we're doing 3 groups of these. I mean, groups of 3 of these. Copy. Actually, let's make it smaller first, because that's not gonna fit that well. Oh, bam. Now we'll copy. There we go. And there we go. There's one group of 3 right there. All right. And here we go. There's 0 groups of 3. All right, now that we understand, let's get back to the video.
Silly, but obviously the correct answer is to just leave the pictures blank. It's a trick question to make sure you're paying attention, but that's what the OP did, and it was marked wrong.
No. Oh my gosh. I guess we have some learning to do. What do you notice? It's impossible to draw a picture. No way. This is like what an adult thinks a 2nd grader writes like, right? Did I write like this when I was 7 years old? It's awful. No.
You can faintly see in red pen how she has kind of circled these problems as if they haven't been completed, and it says on the top, finish.
Finish? Dude, this teacher's having a laugh.
Finish 1A. And it's not like the student just turned in a blank worksheet. At the end, it asks, what do you notice? And OP writes, it's impossible to draw a picker. The presence of this question makes it seem clear that the teacher knows these problems are a little weird, so what was he supposed to do? Oh boy, it's gonna be tough to run defense on this one, but run defense we must. What is the teacher on about? If this is wrong, what was the student supposed to do for these 0 multiplication problems? Well, when 2nd graders are taught multiplication, they're taught to think about it very concretely. Research has shown that jumping into abstract things like pi multiplied together square root of 2 times is an ineffective way to get the multiplication message through to even the most precocious 2nd graders. So how can it be made concrete? Well, like we just saw, we can actually draw out and arrange the objects that represent the multiplication. 3 times 4 is 3 groups of 4. We can see concretely what this operation represents. But a more memorable level of concreteness can be obtained with manipulatives. So I went to the store and bought 40 apples.
I did not pre-watch this video.
Like this so they
apples
can really
is like a standard
like
thing.
Okay?
Sign. Don't accuse me.
What's 5 times 8? It's like 5 groups of 8 apples. In this way, even the groups themselves, not just the 40 apples, are acting as objects we can see and touch and
Man,
crinkle
Apple
and
sounds
cut.
pretty good
If
right
the
now.
students were taught multiplication this way, then maybe it was the teacher's intention for the students to actually draw out the groups on this worksheet. Maybe the students had been taught to represent 2 times 3 as 2 groups of 3, so 2 boxes, each with 3 circles in them, for example. Then,
Okay.
for 2 times 0 on this worksheet, that means 2 groups of 0, so just 2 empty groups. For 5 times 0, we would draw 5 boxes of nothing. And then going
Okay.
back to the top, for
That makes
0
sense.
times 3, we um well, if you just assume that 0 equals 1, then 0 times 3 is the same as 1 times 3. And so obviously the answer would be this. But
Wait, hold on. All right, so we went from 5 empty groups. That makes sense. I'm down with that. And then 0 non-empty groups. How would you do that? So a non-empty group of 3, maybe it would be like this. All right, I got the answer. So we got this, right? And then let's see here. Let's see. Apples are losing their resolution. I wish there was like an outline button. You know what I mean? That would be really convenient. So we're gonna go like this and just pray that I can erase what I want to erase, I guess. This isn't gonna work. This isn't gonna work. Alright, let's try this. Nope. We're gonna go with this. We're gonna go with this. That. See? You see where we're going with this? See where we are going with this? That. Right? You see it? You see it now? Okay, and then we're gonna do another one here. Like so. Down. Mm-hmm. All right. We are getting pretty darn close to section. Okay, almost there. Be patient. There we go. And then we're gonna use this guy again. Oh, bam, 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 bam. See? See, you see? Okay. And then we're gonna zoom in, get some fine detail. I don't know how this thing survived. Okay, and then since the eraser is messed up, we're just gonna use this. And we're gonna just draw a little bit in there. There we go, very nice, very nice. So never say that something is impossible. Message here, right? Just so you guys know. Not impossible. Alright, so we got that going on, and then we got this. Okay. Then I'm gonna zoom back out. See that? You see that? Okay. Then we're gonna get rid of these ones. We could just get rid of these. Get those out of there. And this guy. Control C, VV. Whoa, bam. Oops, actually, let's do one of it. Bam. And whoa, bam. And then do something like this. See how it's like a dotted line. So it's like it's not there. And now we have, can you see it? It is 0 groups of 3. Just like that. Wow. I know it was really it was quite a journey to get here. But that is how you depict 0 groups of 3 apples. Here we go.
We well, if you just assume that 0 equals
0
1,
equals 1.
then
That's
0
ridiculous.
times 3 is the same as 1 times 3. And so obviously the answer would be this. But why would we assume that 0 is equal to 1? I mean, that's hogwash, right? 0 times anything equals 0. So it's simple. There's no need to overcomplicate this. The student should have received credit. But if we think they should have received credit because 0 times anything is equal to 0, so all of these pictures should be empty, well, is that something we can prove? It might seem like a basic fact, but mathematicians love proofs. If we could prove this, then that would show the student's righteousness once and for all. And what if we could prove that 0 equals 1 and show that maybe the teacher was onto something?
This is some crazy stuff
Today,
he's getting
we're
into
going
here.
to do both. You might think that proving anything times 0 is basic math, but you'd only be half right about that. If you want to train up for this sort of thing, check out today's sponsor, Brilliant.org. To prove anything about 0, we're going to have to discuss some fundamental properties of algebra, and Brilliant can take you from knowing these properties as a list of rules to understanding them deep in your very essence. Often, math teachers try to explain the intuitive processes underlying mathematics, but students forget about intuition when they're busy grinding out problems from
The hell was that?
What I love about Brilliant is how when they're busy grinding out
New York Times bestseller from the author of Math Doesn't Suck, Danica McKellar. Kiss My Math. Showing pre-algebra.
when they're busy grinding.
We should use PEMDAS as our guide. You know what this looks like? A lot of reading. I guess there's a lot of reading in a math textbook, but
Out problems from the textbook.
maybe
What I
it's
love
all in
about
the
Brilliant
font.
is how their exercises emphasize simplicity and interactivity in a way that whiteboard demonstrations and textbook exercises can't really replicate. There's a great selection of courses in math and science. For example, the visual algebra and quadratics courses will build on and test your understanding of some of the most critical properties necessary to prove basic and more complicated algebra facts. To learn for free on Brilliant, go to brilliant.org/Wrath of Math, scan the QR code on screen, or click on the link in the description.
Streaming
Brilliant
ads.
has also given Wrath of Math
My,
viewers 20% off an
phone.
annual premium subscription, which gives you unlimited daily access to everything on Brilliant. And now it's proven time. Let's begin by proving 0 equals 1. There are actually many proofs of this fact. For example, here's
This
one from my
fact.
first edition copy of Spivak's Calculus. This proof shows that 2 is equal to 1, and of course, from there, it's a cinch to just subtract 1 from both sides of the equation and arrive at our result. 1 equals 0. But you might have noticed this proof isn't very convincing.
Alright, let's see what's going on here. I mean, I guess he's gonna go over it, but I want to go over it. That's what I think makes some of this guy's videos fun. Alright, let's see. Let x equal y. X squared equals x times y. Okay, sounds good so far. X squared minus y squared equals xy minus y squared. Okay, I think that sounds good so far. In other terms, this would be x squared minus x squared, and xy is x squared, or xx, and xx minus x squared is, okay, it all checks out so far. Okay. Uh, okay, we on the left side here, we've got a difference of squares. So we have x plus y times x minus y. Cool, cool. And then on the right side, we can factor out a y. Very cool. Okay, so we factor out a y and get y times x minus y. Cool. And then what's going on here? Ah, we're dividing both sides by x minus y, and we cancel those out. Now we have x plus y equals y. Interesting. I've never actually done this kind of a silly thing before, on purpose anyway. And it all seems to check out. Very interesting. Then we have x plus y equals y. We substitute y for x, and that means y plus y equals y. And y plus y equals 2y equals y. Why? How did they do this? I didn't see the mistake. There's got to be a mistake. You can't just do this. X equals y. So we have xx equals xx. I forgot what we did here. We subtracted xx from both sides. So it should still be equal. And then here, this difference of squares part is where it gets funky. No. X plus y, x minus y, that's fine. Factor out the... I mean, you're basically factoring out an x, so it's x times x minus x. And then here, there's x plus x times x minus x. I think it's because we're basically saying 0 equals 0, and you can do some funky shit with 0.
We start off by letting x equal y, multiply both sides
I was
by
going to
x,
say exactly
so
what I
x
just said.
squared equals xy, then subtract y squared from both sides. On the left, we have a difference of squares, which we can factor. On the right, we can factor a y out of both terms, then divide both sides by x minus y to get that x plus y equals y. X and y are the same, so x plus y is the same as 2y, and then just divide both sides by y to get 2 equals 1. And then, of course, 1 equals 0. But when we say that x equals y, well, that means x minus y equals 0. So when we divide by x minus y here, that is bad news. Dividing by 0 is the oldest trick in the book. I mean, it can be used to prove anything, even absurd claims like women prefer dating older men because older men have more impressive collections of math books.
True.
If we're going to prove that 0 is equal to 1 and show that that teacher might have been onto something, we're going to need a proof that's a little more compelling. Let's try this. What is an exponent? Well, it's repeated multiplication. X to the power of 2 is just x times x. And what's multiplication? It's repeated addition. Something like 3 times x is x plus x plus x. So that means x squared, which is x times x, must also equal x copies of x added together. So x squared equals this. Now we use calculus. We're going to take the derivative of both sides of this equation. We don't have time to do a calculus intro in this video, but all we need here is what's called the power rule, which tells us the derivative of x to the n is n times x to the n minus 1.
Oh, that's called the power rule?
0. Thus, in the case of x squared, the derivative is 2
I don't remember how to
x to
do
the
the derivative
1,
without that rule.
So x to the 1. And in the case of the derivative of x, well, the unwritten power here is 1, so applying the power rule, we would get 1 times x to the 1 minus 1, so x to the 0. Anything to the 0 is 1, so this derivative is just 1. One other important property we need is the linearity of the derivative operator. So to take the derivative of the right side of this equation, we can actually just differentiate the individual terms. That's not how it works with multiplication. If we were taking the derivative of a product, well then we really need to consider that product. We can't just take the derivatives individually of the two factors. But with addition, it does work that way. So on the left, we have the
Oh, it's
derivative
gonna
of
be
x
1
squared,
plus 1
and on
plus
the
1.
right, we have the derivative of all of these individual x terms. Like we went over, the derivative of x squared, here on the left, is 2 times x. On the right, we have x copies of the derivative of x. The derivative of x is just 1. That means we have x1s all added together, which is just x. Then just divide by x to find that 2 equals 1, and subtract 1 from both sides to find that, once again, 1 is equal to 0. The
Whoa.
teacher then could simply argue that because 1 equals 0, these are the correct answers to the worksheet, and so the student deserves 0 points, so 1 point. We will come back to this argument later, but let's move on to the student's weapon, a proof that 0 times anything equals 0. After all, even if 0 is equal to 1, if the student can show that 0 times anything equals 0, then his answers are still correct. Saying we're gonna prove 0 times anything equals 0 raises one big question. If we can't just assume that 0 times a always equals 0, then what the heck can we assume? We can't just prove this fact out of nothingness. We need some agreed upon truths, and these are called axioms. When doing multiplication and addition with integers, there are a variety of axioms we assume to be true. But let's just look at the ones we're actually gonna need. First, the fact that there is an additive identity called 0. This means that we have this integer called 0, so that if we add it to anything on either the right or on the left, it produces the same number. It preserves its identity. Adding 0 doesn't change anything. If you're ultra skeptical, you might ask, what if it's some other number that has this property? Some number that looks like this? What if it isn't 0? Well, that's not how it works. It's not that 0 happens to have this property, but rather whichever number has this property, that's the one which dons the noble robes of 0. Another axiom we need is that the integers have what are called additive inverses. Take any integer called, say, uppercase.
Can you guys see this? You guys can't see that. That's good. My model keeps messing up. I don't know why. That's better.
J, then there must exist another integer called negative uppercase J, so that when it's added to uppercase J, the additive identity 0 is produced. We'll also need the famous distributive property. This property tells us how multiplication interacts with addition. And keep in mind some of the versatility of the distributive property. Yes, we can distribute a factor through a sum in the parentheses, but we can also go the other direction, taking a common factor outside of a sum. And we can take that factor out on the left, or if we prefer, we could take the factor out on the right. Those are all the axioms we need. We're going to start with 0 times an integer k on the right, and we're going to apply the properties we just discussed to eventually arrive at equals 0. You might want to pause the video now and try to see if you could save our unfortunate second grader and prove that this equals 0. If not,
Okay, so we have 0 times k. How do we want to prove it? Let's suppose k is some real number. So we have 0 times some real number k, and this equals, let's say, some non-zero real number, x. We'll just use x. All right, so 0 times k equals x, where x is non-zero. Alrighty. So, is 0 times k... Okay, I have to write this down. I have to write it down. Because I can't just freaking juggle this in my head and then, like, have it be juggling in y'all's heads. Alright. Let's get this stupid shit out of here. This isn't stupid. This is actually genius level stuff. I've got an IQ of 79. Okay, so we'll go here. And we got... Just make this tinier. Alright, so we got 0 times k, and we're gonna not use x because it looks like the times. So we'll use b because so 0 times k, where k is a real number. I don't remember the notation, but it's is in boom boom that, and b does not equal 0. So I don't remember what this type of proof is called, but we're supposing that, like, the opposite of what we want to prove, right? Okay, so what we can do is, what can we do here? So he suggested that we have 0 as the additive identity. So there's that. Okay. And then he also suggested using the distributive property. So let's try that. Let's try adding 0 to both sides, right? So we're going to go ahead and we'll go ahead and do this. Bam. Actually, let's shrink this all down. We're going to need some space for this shit. All right. So I'm going to go bam. We're going to copy that. I'm going to paste it down below. And right there. And then we'll do something like that. And we'll copy this. And paste that down below like that. All right. And we're going to add, oops, 0 to both sides. Okay. So they should still be equal. We haven't done anything to one side that we didn't also do to the other side, so we should be good. Now, we've got 0 times k. Oh, we could put this in parentheses because, you know, just to keep things all nice and neat, right? Oops, that looks like a 2. Okay. Hmm. What am I doing here? Oh, I wonder if instead of adding 0 to both sides, if we should multiply 0 to both sides. Let me think. I don't know if we could do that. We could subtract b from both sides. We could try adding some other value to both sides. This is how I did my proofs back in school. I just try shit out, and eventually figure something out. And then over time, you learn what you can and can't do, or like what'll lead you down the right path. But I've forgotten all that stuff because it's been a long time. Let's see. Wrath of Math, though, he does this shit all the time, I guess. Alright, let's simplify this stuff. Let's go ahead and 0 times k is 0k. And then we have plus 0 equals b plus 0. And remember, b does not equal 0, is what we're assuming, right? But what we do have over here is something that we can work with. So we can factor out this 0 times k plus 0 equals b plus 0. And something that I would be wanting to do is dividing both sides by 0, but we can't do that, can we? Oh, but actually, we do have... Oh, well, actually, we had the additive identity from the very beginning. K plus 0 equals k, right? And b plus 0 equals b, and we're back to where we started. So we don't want to do that. Let's try this. Let's divide both sides by k plus 0 and k plus 0. And so we have 0 equals b plus 0 over a plus 0. Looks a little too much like a 6. There we go. Can we do anything with that? If we subtract this from both sides, we have 0 equals this thing, and then we would get 0 equals negative this thing, and we're more or less where we're at anyways. If we multiply both sides by k plus 0, we get back to 0 times k plus 0 on the left side, and just b plus 0 on the right, which is the same as this, I think. Or actually, we just go right back to where we were right here. That's not what we want to do. What did we determine again? K is a real number and B is something that's not 0. So what we want to happen is get K equals B. I don't remember how to do proofs. Sorry, we'll have to find the answer over here. Wham.
No worries, let's go ahead now and fill in the details. If you don't mind, just for the cleanliness of this presentation, let's omit the multiplication sign. So 0 times k, we'll write like this. Then we know that without changing the value of this expression, we can add 0. We know that because there's an additive identity and its name is 0. Then remember one of the ways that we can produce 0. If we combine additive inverses, we get 0, that additive identity. So if we wanted to, which we do, we could replace 0 with 0 times k minus 0 times k. Then here we can apply the distributive property.
Wait, what just happened here?
0 additive identity. So if we wanted to, which we do, we could replace 0 with 0 times k minus 0 times k. Then here we can apply the distributive property. We have 0 times k plus 0 times k. Let's go ahead and take a k out of that, and we're going to slide it out to the right. Thus, we now have 0 plus 0, and we've slid the k out of the parentheses using the distributive property, and then minus 0 times k. Just to be pedantic, let's write that like this: plus negative 0 times k. Now, what's 0 plus 0? Well, adding 0 doesn't change anything, so this is just 0. Hence, we can write this as 0 times k plus negative 0 times k. But then this and this are additive inverses. They combine to produce what else? Of course, it's 0. And with one more axiom, the commutative property of multiplication, we know that order of multiplication doesn't matter. So not only does 0 times k equal 0, but also k times 0 equals 0. Now there's no denying it. The teacher unfairly and illegally stole this student's points. He should have earned full credit because indeed all of these products equal 0, and so all the boxes should be empty. I wish we could go back in time and see how the teacher would argue this grading. If the student asked, "What was I supposed to have written?" what would she say? We do have some anecdotes in the Reddit thread of people with similarly baffling grading issues. Let's see how these played out. This guy says, "Reminds me of my second grade English teacher who denied me the chance to get 100% on every assignment because she said pickle was only one syllable and not two."
What?
You, Mrs. Johnson. My 6th grade English teacher told me colloquial wasn't a real word. My English teacher told me bizarre wasn't a real.
What the? See, this is what I was talking about yesterday, dude. There are really good teachers out there, and there are really ridiculous teachers out there, and I feel like there's not very much in between. Kind of like people.
Word, and then gave me detention when I showed the dictionary entry to him. At least good ending here, the detention was canceled once she explained to the headmistress that it wasn't her fault that the teacher looked stupid. My teacher in 5th grade forgot to use an apostrophe on the blackboard, and when I raised my hand to let him know, he sent me to in-school detention. This person also got a small amount of justice by being sent back to class because they couldn't be punished for being correct. Man, with teachers like that out there, maybe someone actually is teaching that 0 equals 1. So I suppose we better clear this up. What's the error in this proof. Naturally, your eyes might jump to the division by x at the end here and think, well, what if x equals 0? Surely this would be a problem. But it's really not a big problem. I can just say, assume that x is greater than 0. Because the things we're considering are functions. X isn't some unknown that sneakily is already equal to 0. X is a variable that can take on infinitely many different values. So if that's not the problem, then what is? Well, we can point to two big issues. Restricting x to be greater than 0 is not a problem. But there's another significant restriction that's implicitly forced by how we've gone about this. Does x times x squared, really equal x plus and so on, x times? Yes, but only if x is an integer. Whereas in the function x squared, even if we assume x is greater than 0, it's certainly not the case that x has to be an integer for this function to make sense. This is a graph of y equals x squared with x restricted to be greater than 0. But if we look at the function from the right side of the equation, where x has to be an integer, this is what it looks like. This is x equals 1, y equals 1, x equals 2, y equals 4, and so on. As you can see, it's way different from the function on the left. And importantly, since we are taking derivatives, the function on the left can be differentiated. Let's give a quick explanation of the derivative, just to make sure that this point is clear. The derivative of the function takes on different values at different points of the function, and the idea is that at each point of the function, the derivative gives us an idea of the slope of the curve. Everybody's familiar with slopes of lines, because that's really straightforward. A line just goes in one direction at the same rate forever. And to find its slope, we take the rise and divide it by the run. In other words, that's the change in y, written as delta y, divided by change in x. On curves, this simple definition doesn't work so well because curves change direction as they go. So the way we get around that with the derivative is to look at the point where you want the slope and then consider some point that's nearby. We can then draw what's called a secant line through those 2 points. The slope of this secant line gives us an idea of what the slope is at this point. To get a better idea of the slope, take a closer point and look at that new secant line. By taking points closer and closer to the point we're actually interested in, we can get secant lines with slopes that are approaching what we consider to be the slope of the function, or the derivative, at this particular point. The key is that to find the derivative at the point, we're looking at secants through increasingly closer points on the curve. But that's just not possible with this function on the right, closer.
Okay, I'm sure he'll still get to it, but the idea is he's getting closer and closer to the thing until you're looking at the tangent line of that point, which will be the slope at that point. And dude, if you're taking pre-calculus or calculus, this is actually a really good video that can kind of speed up some of your learning, because it took me so long to understand what the fuck we were doing in calculus. Like, you start learning the formulas and all these things, and you just don't wrap your head around what you're actually doing until like the following semester, when you're in Calc 2 or something. At least that's how it was for me. Like, I'm a really slow learner. And yeah, wrapping my head around this took forever. But yeah, this is really good. Really good visual, really good explanation of one of the kind of uses of a derivative, or what the information is that it's given you.
Points on the curve. But that's just not possible with this function on the right, where x has to be an integer. Let's say we want to take the derivative right here. Okay, well then I can draw a secant line through this other point over there. That gives me an approximation of the slope, but it's certainly not the derivative. And that's really my only choice. I can't get any closer to this point because there's no closer points on the function. So for this function, the derivative does not make sense. So we tried to exploit a certain
I don't
way of
understand,
writing
actually.
x squared, but writing it this way implicitly has important restrictions that this proof does not account for. The other more significant issue is also more subtle, and that's the fact that we can't simply differentiate each of these terms individually. And that's because the entire sum depends on x. If we just have x plus x and that's our expression, then it's no problem at all to differentiate this entire sum by taking the derivatives of the two terms individually. How much change in x is there per change in x? Well, of course, they're the same exact quantities, so the answer is 1. X is the same as x, so as x changes the exact same way. Same thing over here, the derivative is 1. The big difference with x plus, and so on, x times, is that the sum's structure itself depends on x. In the simple expression x plus x, what happens if x increases by some small amount, delta x? Well, each of these terms will also increase by delta x. Simple. But over here, if x increases by delta x, it's not just that each expression increases by delta x, but the number of expressions itself increases by delta x. It's completely different. And because the structure of the sum itself changes with x, we can't simply differentiate it with respect to x term by term, because then we'd be failing to take into account the change in the number of terms. And when we're taking derivatives, we need to account for all of the change caused by the independent variable. So lo and behold, 0 doesn't actually equal 1. And with that established, I'm finally confident in saying I have no clue what the teacher expected the student to write in these boxes. If you have an idea, please share in the comments, and maybe with all of our combined energy and professions of saintliness, we can summon the students' lost points from that sullen moment of the past wherein they were unduly ripped from his worthy hands. And be sure to subscribe for more of the swankiest math videos on the internet.
All right, what do people say? We need calculus. Okay. Okay. So, just so y'all know, that explanation of the latter problems, let's just say problems, with x groups of 0 were correct. And for the 0 groups of x, we simply suppose x is represented by some physical object, say apples, and depict these apples without their color filled in, and with a dotted outline indicating that there are indeed none of those would-be objects. You're welcome. Man, somebody's gonna take this comment seriously, and that could be fun, huh? Ah, sheesh. My model fucked up again. Come on, stop it. Get some help. Right, hopefully. Well, that worked for all of a moment. Alright, so we got that. Turn it back on. It's on. Give it some time. I think I have to turn the camera off long enough, I guess. Come on, what is going on? Well, it's decided it doesn't want to work. Weird. Like the inconsistency of it is really strange. Well, gonna look still for a while. Comment. There we go.